Okay, we're going to start on section 8.1, and we're going to start with problem number 8. And so this is kind of a review of our things that we've already done. So let's just write number 8 down. And what we're trying to do is we're trying to identify these as something that we can rewrite in terms of U and use a basic integration rule. So it's just U substitution. So as we pointed out in class, this one has the form of something squared plus something squared in the denominator, which is the arctangent. And if you look on page 520 at number 819, we see this particular integration rule. That the integral of du over a squared plus u squared is equal to 1 over a, the arctangent of u over a plus c. So that's number 19. So we can kind of see, hopefully see this, that this part would be u. So we're going to let u equal 2t minus 1. So we calculate du, which is just going to be 2 dt. And then we look at the original equation and see how we're doing. Well, this part is going to be du. This part is going to be u, and this part is going to be a squared. So we can say a is equal to the square root of 4, which is 2. And therefore the original equation can be rewritten as du divided by, and it doesn't matter which one's first, so we're going to say u squared plus a squared. And so that fits the rule. So we do the integration using the rule. And then the final step is to substitute back in for u in terms of what we decided u would be, and a. So we get 1/2 the arctangent of 2t minus 1 over 2 plus c. So that's the final answer. Okay, this is problem number 10, section 8.1. And so what we're asked to do is find the integral of negative 2x dx divided by the square root of x squared minus 4. A lot of times the u that we want to use as substitution is the term that's in a parentheses or in a square root. So the first thing we try is this. We try that x squared minus 4 is u, and therefore du is just 2x, which is the derivative of x squared, and then times dx. And then we look back at the original equation, we see we have 2x dx. So this can be du, and this can be u. So before we do the substitution, let's factor out a negative 1. So at this point, we can use the two substitutions we have, and so this equation will just become negative the integral of du over the square root of u, which is the same as negative the integral of u to the negative 1/2 du. Because this is just a simple power rule, we have a rule for that. And the integral of u to the minus 1/2 would be u to the positive 1/2 as we add 1 to the exponent, and we divide by the new exponent. And we add our arbitrary constant. So dividing by 1/2 is the same as multiplying by 2. And then finally we can do the substitution back in. We can use u as x squared minus 4, so we get negative 2 times x squared minus 4 to the 1/2 power plus our arbitrary constant c, And then finally, we can rewrite u to this to the 1/2 power is the same thing, x squared minus 4. And that is our solution to the problem. And this is problem 13, chapter 8, section 1. And the integral that we're trying to find is the cosine of x times e to the sine of x dx. Of course, we do not have a simple integral rule that handles this one. But if the exponent of the e term is something other than x, then a lot of times the exponent is the u. So we would let u equal the sine of x and see if that works out. So du, the derivative of the sine of x, is positive the cosine of x times dx. So you see that we have these two terms make up du, and then we'd have e to the u. So we can rewrite this as e to the u du, which we do have a simple integral rule for that, and the answer is e to the u plus our arbitrary constant c. And we substitute u back in, and so that is the result. This is problem 22, chapter 8, section 1. So just like the previous problem, problem number 10, we would initially think that this would be our u, and then we would check to see if that works. So we're going to let u equal the expression inside the square root. Therefore, du would be equal to 2x plus 2, the whole thing times dx. And we look at the original expression, we say we have 1x plus 1 times dx. And hopefully we would recognize that if we multiplied both of these by 2, that we would get to a form that we could do the u substitution. So we will do that, and we'll say we're going to multiply the outside by 1/2, which allows us to multiply the inside by 2. So instead of x plus 1, we get 2x plus 2 divided by the square root of x squared plus 2x minus 4, the whole thing times dx. And you can see this term is du, and this is u. So now we can do the u substitution, and we have du over the square root of u. And so that's the same as u to the minus 1/2 power du. And when we integrate, we get 1/2, which is the constant, times u to the 1/2 power divided by 1/2 plus arbitrary constant c. And you can see we can multiply 2 in the denominator by 1/2 in the denominator, which will give us 1. So we just have u to the 1/2 plus c. And now we can do the substitution back in. And I'm just going to go ahead and do it all in one fell swoop here. So we have x squared plus 2x minus 4 plus c. So this is u, and 1/2 power is the square root. This is problem number 25, chapter 8, section 1. So we look at this and we think about what choices do we have as far as u is concerned, and notice that the exponent of e to the x is just x. So it's not going to help any by choosing u to be x. So the other options would be e to the x, but we know that the derivative of e to the x is just e to the x, so that doesn't help us out. So our last choice is going to be that we're going to let u equal the denominator. And so when we take the derivative, we'll get 0 plus e to the x dx. And then we look back at the original equation and say, okay, this is u and this is du. So we can then make those substitutions. The numerator becomes du, the denominator becomes u. This is one of our integration rules, which is the natural log of the absolute value of u plus the arbitrary constant c. And then we make the substitution back in, u is 1 plus e to the x. And that's all we can do. You might think, well, we can do something here, but we can't because this is 1 plus e to the x. If it was just e to the x, then yes, we could use the inverse properties of logarithms and exponentials to get x. But because we have this plus sign, we can't do anything. So this is the final answer for this problem. This is problem 27, section 1, chapter 8. When we have a trigonometric function, a lot of times the term inside the trig, the argument of the trig function, is the u. So we're going to try that in this case. So we'll have 2 pi x squared. So when we take the derivative of that, 2 pi is the constant, and then we'll get 2 times x times dx. So let's multiply that out. We'll have 4 pi x dx. So now we look back at the original expression. This is u. We have x dx. And if the only difference between x dx and du is a constant, then we can just rewrite the original expression as such. So we need 4 pi. So we've got 4 pi. So we have to divide by 4 pi so that when these are multiplied together, you get 1. And then we'll have x times the cosine of 2 pi x squared dx. 4 pi x dx, 4 pi x dx is du, and this is u, so we can say that's the cosine of u du, which we have an integral for, which is the sine of u, plus the arbitrary constant. So we'll have 1 over 4 pi times the sine of u plus c. And then we can substitute back in for u, and that was u was equal to, it's right here, 2 pi x squared. So we'll have 1 over 4 pi times the sine of u, which is 2 pi x squared plus c. Okay, we're going to do problem number 41, chapter 8, section 1. So this is one of those Pythagorean identity problems. So we're going to do the math on the identity first, and then we will, once we rewrite this in a form that we can integrate, then we'll put the integral sign next to it. So if we take 1 over cosine of theta minus 1 multiplied by the Pythagorean conjugate, so that means we add 1. So this is subtracting 1. We do this to both the numerator and the denominator. So we get the cosine of theta plus 1 divided by cosine squared theta minus 1. And if we remember Pythagorean identity, sine squared theta, cosine squared theta equals 1. That means that cosine theta minus 1 is going to be equal to negative the sine squared of theta. So we can rewrite this as the cosine of theta plus 1 divided by negative sine squared of theta. And let's put 2 pages up here. And so probably the best thing to do is to look at this and rewrite cosine over, so we'll have cosine of a negative sign, negative cosine of theta over the sine of theta times 1 over the sine of theta minus 1 over the sine of theta quantity squared. So we get negative the cotangent of theta times the secant of theta, and this will be 1 over the sine is the cosecant, so we get the cosecant squared of theta. So that is the result. I'm just checking to make sure I did it correctly. Okay, so we're good. So our original integral now, instead of 1 over cosine theta minus 1, is going to be equal to negative the cotangent of theta, cosecant of theta, minus cosecant squared of theta, the whole thing times d theta. So we just have 2 integrals. And if we go to page 520, we see that the integral of the cosecant cotangent is negative the cosecant. So the integral of this will be negative the cosecant, and we have a negative sign, so that'll come out to be positive the cosecant of theta. And then the cosecant squared, the integral of that is negative the cotangent, so that will become negative times a negative, so it'll become positive the cotangent of theta, and then we add c. So that's one way of doing it. We could also just rewrite this as one fraction, and so what we would have is 1 over the sine of theta plus cosine of theta over the sine of theta. Cotangent is cosine over sine. And so that would be 1 plus cosine of theta over the sine of theta plus our arbitrary constant c. So that's another version. That would be completely acceptable. This is problem 64, problem section 8.1. So this is a definite integral, but we still are using these techniques of integration to solve the problem. And we were talking about this the other day from hints. We know the derivative of the natural log of x is 1 over x, so it might make sense to make this du, and therefore this hopefully will be du. So we're going to let u equal 1 minus the natural log of x, and therefore du is 0 minus 1 over x times dx. So we don't have negative dx over x, so we would take the original equation, we would factor out a negative 1. We'll leave this, we'll put a negative sign there, so it's negative 1 over x dx. So this integral is going to be the integral, and we're going to, the question is, do we rewrite u? So let's do that. Let's change our limits of integration from x to u. Then we don't have to, then we can just solve it in terms of u. So when x equals the lower limit, when x equals 1, u equals 1 minus the natural log of 1, and the natural log of 1 is 0. So u equals 1. And when x equals e, we get u is equal to 1 minus the natural log of e. And the natural log of e is 1, so we get 1 minus 1, which is equal to 0. So we have negative sign from our lower limit was x equals 1, so our lower limit is u equals 1. And our upper limit is u equals 0 of u times du. U being 1 minus the natural log of x, du being negative x dx over x. And one thing we can do is, I mean, 6 1 1/2 dozen the other, but we can change the limits of integration. So if we make that positive, we can switch the limits of integration. So we integrate from 0 to 1 of u du. And that's equal to u squared over 2 evaluated between u equals 0 and u equals 1. So we will get 1 squared over 2 minus 0 squared over 2, which will be 1/2. And this was problem number 64. So I'm just checking to make sure I did everything right. So that is correct, yes. The other way would we would plug u back in here. So we'd have 1 minus the natural log of x, and our limits would be from x equals. Now we'd have to be careful here about this. We wouldn't do this thing. We wouldn't switch the order around. Let's go ahead and do that just so everybody's clear. So the other way to do is we would, when we get to this point, we would leave the limits the same. So it would be from x equals 0 to x equals 1 of u du. So we'd have negative x squared over 2 integrated between 1. Oh, let's fix that here. Hold on just a second. So I changed the limits here. I changed them to u. So really, the limits are whatever they were to start off with. So it's actually just from 1 to e. So let's put that in there. So I'm keeping my x limits, and I'll just hold them around until I make the substitution back in. So my limits are still in terms of x. Now I would stick back in u. U would be equal to 1 minus the natural log of x squared divided by 2. And that would be evaluated between x equals 1 and x equals 2. So we can evaluate the limit now because this is the limits are in terms of x and the equation is in terms of x. So let's put a minus 1/2 out in front. And so the upper limit would be 1 minus, I wrote 2 there, I don't know why I wrote 2 in there. So e, okay, so the upper limit would be 1 minus the natural log of e, quantity squared, and then we'd subtract off the lower limit, 1 minus the natural log of 1, quantity squared. Okay, so we have negative 1/2. And we would have 1 minus the natural log of e, which would be 1. Square that, minus 1 minus the natural log of 0, which is 0. We square that. And so we'd have negative 1/2 times 0 minus 1, which is positive, because we have a negative times a negative, positive 1/2. Same answer we got previously. Okay, problem 65, chapter 8, section 1. We look at the terms in parentheses or in square roots as a good first choice of u substitution. So we would try this first and see if it works out. So when we take the derivative, we'll get 2x dx. And you can see we have 2x dx, so that matches up exactly. And what we're going to do is we'll do it 2 ways. We'll do it where we change the limits and where we don't change the limits. So if you're happy after I don't change the limit, after I do change the limits, then you don't need to watch the rest of the video. So it's just for the people who prefer it the other direction and looking for errors they might have done. So we have to change our limits first. So x equals 0, u is equal to 9. X, so we just put 0 in and we get 9. X is equal to 4. We get u is equal to, that'd be 16 plus 9, which is 25. So because this already matches up identically, we don't have to do anything to it. So we can just rewrite the integral as the integral from 9 to 25 of du, which is 2x dx, divided by the square root of u. And of course that is the integral from 9 to 25 of u to the minus 1/2 power du. And so when we integrate it, we get u to the 1/2 power divided by 1/2, which is the same as 2 times u to the 1/2 power. And we evaluate that between u equals 9 and u equals 25. So we would have 2 times, and that's just the square root of u, so we'd have the square root of 25 minus the square root of 9, which is the lower limit. So we'll have 2 times 5 minus 3. 5 is the square root of 25, 3 is the square root of 9. So that's 2 times 2, which is going to be 4. And just checking. Okay, so that's right. Now, if you wanted to not change the limits, what you would do is you would, when you get to this point, we would keep the limits the same. And I'm going to explicitly show that we're not changing the limits. But we'd still be u to the minus 1/2 power du. So we integrate that, and we get u to the positive 1/2 divided by the new exponent. We evaluate that between x equals 0 and x equals 4. So then we substitute back in for u. U is x squared plus 9, so that becomes x squared plus 9, and the whole thing's square root. And dividing by 1/2 is multiplying by 2. And we evaluate that between x equals 0 and x equals 4. So we haven't changed our limits at all. We just kept those constant while we, or steady while we go through here. So now we evaluate it. So what we have is the square root of 16 plus 9. That's evaluating this at the upper limit. And you subtract off at the lower limit, which is 0 squared plus 9. So that becomes 2 times the square root of 25 minus the square root of 9, which is 2 times 5 minus 3, which is 4. Okay, this is problem 67. I just did it and I realized I had the limit wrong. So I'm not going to rewrite the whole thing, I'm just going to explain it. So the problem is we have the integral of 1 over 4 plus 9x squared dx from 0, x equals 0 to x equals 2 over the square root of 3. And it turns out, let me just go one step here, that this fits the form of the arctangent, and this is the rule for the arctangent. So we need to define a and u. So a is going to be the square root of 4, and u is going to be the square root of 9x squared. So u is 3x, and a is 2. So we know the integral, it's going to be 1/2 the arctangent of 3x over 2. But we're going to substitute, we're going to change the limits for u, and we're also going to make sure we have du working out correctly. So that's one thing we have to keep an eye on. So du is the derivative of u. So we get 3 times derivative of x, which is 1. So we get 3 times dx. So we only had 1 dx in the original equation. So we multiply by 3 to get 3 dx. We have to divide by 3, so those cancel out and become 1. So that's the integral that we're going to do. We're also going to change the limits of integration to u.
Okay,
so the lower limit,
so this is starting off chapter 6, problem number 20.
0. The upper limit is 2 divided by
And what we're doing in the next couple of problems is we're just verifying that this particular equation, the differential equation,
so plug in
y prime
x into there,
minus
3 times
2y is
divided by
equal
the square root of
to
3,
x cubed,
which is 6 divided by the square root of
to
3,
the
and
x.
multiply by the square root of 3 over the square root of 3.
That's the
You get
differential
6
equation. We're
squared
asking
3,
if
which is 2
this
times the square
particular
root of 3. So
case, y
that's our
equals
new
x
limit
squared
of
times
integration when we do the
to the
substitution.
x, if this is a solution to this differential equation. So basically what we do is we have y already, and we calculate y prime by taking the derivative, and then we substitute in for y prime and y, and this, once we simplify it, the left-hand side equals the right-hand side.
0 to 2 times
then
the
we
square
verify
root
that, and then we say
of
this
du over a
is a
squared
solution to that differential.
So the result is
equation.
1 over a, but we have, since we have 1/3, it's 1 over 3a, the arctangent of u over a.
Okay, so we're in section 6.2 now.
Tangent 0, 0. So we only have to
And this is using, I'm not sure if we call it separation of variables or not, but
3 times 2.
see, are we calling it?
Since a is 2.
Talking about
Arctangent of u. Yep,
we'll get the separation of variables in the next section, but
divided by a.
we're solving differential equations kind of like we did before.
The arctangent of the square root of 3.
Okay, so we're going to do number 2.
And the angle tangent is the square root
so
of 3.
So 2 has, here's our differential equation.
So we have 1/6 times
and
pi over 3.
We're not giving,
and that gives us pi over 18. Let's just do it again. I didn't get this far.
Okay, so this
substitution back in.
Section 6.3, which basically is separation of variables.
You would have the limits.
Also, logistic growth equation.
Here, and we have 1/3, and I put
homogeneous equations, which
x equals 0 to x equals
are equations that initially cannot be solved by
2 divided by the square root of 3, and of du over a squared plus u squared. And so what we would get is we get 1 over 3a, the arctangent of u over a, evaluated between x equals 0 and x equals 2 divided by the square root of 3. When we substitute u back in, u is 3x and a is 2, so we'd have 1/6 the arctangent of 3x over 2. And now we have the limits match the variables. So now we plug in. Again, the lower limit's going to go to 0 because the arctangent of 0 is 0. So all you have to do is evaluate at the upper limit. So we'll have 3 times x, which is 2 divided by the square root of 3, the whole thing divided by 2. And so the 2's cancel out, and you get the square root of 3 over 3, which is just, if you multiply, so let's do that, arctangent. So the 2's cancel out, and you get 3 divided by the square root of 3. But if we multiply the numerator and the denominator by the square root of 3, this is 3, and these two multiplied together is 3. So we just end up with the arctangent of the square root of 3. And if you remember the way the tangent function goes, we have 0, pi over 6, pi over 4, pi over 3, and pi over 2. This is a tangent of the angle in radians. Is 0, and we get the square root of 3 divided by 3. Here we get 1. Here we get the square root of 3, and here it's infinity. So, so that's the 1. So this is going to be equal to pi over 3. The angle whose tangent is the square root of 3 is pi over 3. So we get pi over 3 times 1/6, which is pi over 18.